Hey everyone, welcome to the video. In this series, we have the honor of inviting Professor Steven Kahn, who has been an astrophysicist and cosmologist for more than 40 years. He is also the director of Vera C Rubin Observatory and the Dean of Mathematical and Physical Sciences at Berkeley University. Let's go find out.
My name is Steven Kahn. I'm currently the Dean of Mathematical and Physical Sciences at the University of California, Berkeley. I'm a physicist and astrophysicist by training. I was an undergraduate at Columbia University in New York and a graduate student at Berkeley in physics in the 1980s or the late 70s. I've been a professor at a number of universities. I've always been an astrophysicist. I began my career working primarily in X-ray astronomy, which involves the study of stars and galaxies and astrophysical objects in the X-ray band of the spectrum. X-rays do not get through the Earth's atmosphere, so that's inherently a space-based discipline, and really began in earnest primarily in the 70s, around the time I was doing my PhD, when satellite experiments first became available. X-ray light is of interest in astrophysics because it's a higher energy form of radiation, and it's only emitted copiously by rather exotic objects in the universe like black holes and neutron stars and supernova remnants and those things. Within that field, I sort of pioneered the development of X-ray spectroscopy, which involves the study of X-ray light from cosmic sources, but in terms of its component colors. How much radiation is emitted at each wavelength of X-ray light. And that gives you very detailed information about physical conditions in the objects you're studying, temperatures, densities, how the gas is ionized, how the radiation is produced. So when I started working in the field, this was very much in a primitive state for a lot of reasons. First, because we didn't really at that time have the instrumentation available to really analyze the cosmic data very well. The X-ray fluxes or the intensities of cosmic sources in X-rays are very, very weak. And so you need highly efficient instrumentation, and of course it has to be in space. So I concentrated a bit on developing that. The other thing was that the conditions that occur in exotic astrophysical sources like black holes and neutron stars are very much different than the physical conditions we have here on Earth. And therefore, the detailed atomic processes that gives rise to X-ray light are exotic. They're not something we've reproduced in laboratories on Earth. So I and my group had to develop the appropriate models and the laboratory experiments to test those models to essentially understand how to interpret the X-ray spectra that we were collecting. And so that was a big focus of my research program in the 80s and early 90s. I also developed what was one of the pioneering first major experiments in X-ray spectroscopy of astrophysical sources, which was a project called the Reflection Grating Spectrometer that is flying on a European Space Agency mission, which is called XMM Newton, the XMM Newton Observatory. That mission was launched. That was a very large mission. It was essentially, roughly a space mission. The piece that I designed and developed was the first sort of reflection grating spectrometer used for X-ray spectroscopy in the space mission. And the XMM Newton flew in December of 1999 is when it was launched. It's actually still in operation, so it's now been 24 or 25 years later. And it produced a lot of the very first X-ray spectra of cosmic sources. So that was an extremely exciting time for me. Was a principal component of my research through the early 90s. But around that time, I got interested in another area of astrophysics, which is fundamental cosmology, the study of how was the universe born and how did it evolve over cosmic time. And in particular, I got interested in doing ground-based optical surveys of the entire sky. So there was a project that at the time was called LSST, the Large Synoptic Survey Telescope, which was a concept developed in the late 90s but really people weren't thinking seriously how to build it until the early 2000s. And so in 2003, I moved from Columbia University to Stanford with a connection to SLAC National Accelerator Laboratory. And I engaged a team at Stanford to work on that project. And that's a very large project. It's $1 billion ground-based telescope. I started working on it in the early 2000s and eventually became director of the whole project in 2013. And during that time, we fleshed out this concept of how to build a very big telescope that was capable of taking detailed images over the entire sky and doing it rapidly enough that we would accumulate a lot of data. And the project was still in construction, but it's nearly completed. And it's now called the Vera C Rubin Observatory. It's based in Chile, in central Chile. And it will provide the largest and most significant time domain and full-scale imaging survey of the whole southern hemisphere. And the science that will come from this telescope is quite broad, but the area that I was interested in when I got involved was experimental cosmology. And that it feeds into that because having very large samples of imaged galaxies allows us to develop fairly stringent statistical tests on the spatial distribution of galaxies and their shapes. And that's intimately tied to a detailed understanding of how the universe has evolved over cosmic time.